Hello everybody. So what we're going to do now, I'm going to show you a bit of a practical example of what we can do with the vectors that we've sort of learned up till now, the vector maths we've been discussing, how to sort of add vectors, subtract vectors, and how this can actually be useful in a 3D situation. So I have here a simulation that often you'll sort of come across and need to be able to sort of recreate. Is the effect of having particles kind of obeying where you would like them to go, and particularly following an object. But following 100% precise is very easy. You know, having something just stick and follow is easy. What becomes difficult is when you want something to sort of follow, but in a way that it has a bit of maybe naturalness to it, or it allows some additional forces to be applied. So like we have here, these particles are kind of almost buzzing around. They're like, I've got them named like fireflies here, or you can think of them as like bees or little insects, or they could be kind of sparkling kind of little magic things, or whatever it is. There's a variety of different ways we could apply this, but ultimately we have these particles essentially following a sphere that I have just animated, right? Moving in a sort of an arc, an S shape. But what they're doing is kind of buzzing around the sort of perimeter of the sphere and doing their own thing, just sort of vaguely keeping nearby, but they are allowed to move a certain distance away from them, from the center sphere. And then when the sphere starts to move, they begin to follow, right? Some of them follow more strictly than others, but the whole swarm essentially follows along with. And you'll see that even while it's moving, there is still, it is kind of harder to see, but there is still that kind of natural random movement happening within that time as they're following. And even when it comes to rest, some of them, go back very quickly to just kind of buzzing around in the general vicinity. Okay. So it's a kind of a nice way of having something follow, but more naturally. I mean, you could have schools of fish as well, or, so like that, there's kind of effects that we have where you've got like, maybe like a school of fish forming different shapes, like a hand or whatever. You can have an animated sort of blend target, but you want the individual members that form that shape not to be too perfect in the way that they form that shape. Otherwise, it looks unnatural, right? If it is literally a hand formed from a school of fish, then you need them to kind of move like fish would, but then at some moments, they need to form that shape. So this is how we can do it. Okay, so we're going to jump in and have a look at what's happening here. And it is quite simple. Really, it just comes down to the vector maths. Okay, so we've got a sphere. I'm calculating some normals. That's all really simple. Also here, I'm just drawing a curve. So the path that I wanted to follow, I'm resampling and smoothing and carving, and then I'm animating that carve here with set to extract. So it just literally has a point moving, and then I'm copying that sphere to that point. So really simple way of getting a sphere to be animated. Okay. Then on that sphere, I'm scattering some points. Now remember, this is on the sphere that is not moving. Okay, so this is non-time dependent. I'm scattering 1,000 points. And then when I'm scattering, I am switching on my primnum and my prim UVW, right? And I'm using attribute interpolate to make it move along with it. This is a technique that you should have probably come across by now, but if not, this is something very useful for having scattering that doesn't recede as the object deforms. Okay, in this case, we don't have deformation, we only have transformation. But either way, it's sort of whenever you have a moving object, and particularly when it deforms, what you want to do is freeze it on one frame. Okay, here I don't have to freeze it because I know that it's at rest, but otherwise you'd have your animated object, you freeze it, you scatter, you switch these two on, and then in your attribute interpolate, you also reference the same source prim and source prim UV, and it interpolates the animation onto those points. Okay, so now they move, but it's the same number of points, and their point numbers are not changing every frame as well. which on a deforming object, you'll see that the points will jump around and reseed themselves, which is not what we want. Okay. So now, on that, I'm freezing it on the first frame. And the reason for this is because that is going to be my source, right? In my sim, I want to just source on one frame, source all 1,000 points just once. And then I want to control where those points are, right? And that's because if we're going to be, let's say, copying the fish onto these points, or bees, or whatever it is, this little swarm that we have, we don't want to be constantly sourcing, because it's not like fish, suddenly appear and then disappear, right? So we can't treat them like we would with normal particle sim. We have to make sure that we source once, there's 1,000 points, and that's it. There's none being deleted and there's none being created, right? And then, not on my frozen geometry, but on the moving geometry, I want to just calculate the velocity, right? So I'm just trailing to calculate velocity. And I'm feeding that into the second input, because I'm going to be referencing these positions on the sphere as essentially my target. So we have 1,000 points here and 1,000 points here, but these are the ones that are moving and these are the ones that are not. These are my source, but they each have a corresponding point on this geometry where they want to essentially be, okay? So they're starting here, but they know where they should essentially live, okay, where they want to try and get near. Okay, so with all of that, we dive inside of our sim, and then I'll show you what we have. Now, I'm just got a basic pop sim setup. I don't have a pop source, because what I'm doing is I'm sourcing my initial geometry, so I'm sourcing just once, okay? This has a few downsides, obviously, like it doesn't age the particles properly and give them an ID and everything. It just it pulls them in, so we have to do all of that work outside. We could, if you wanted to source, use a pop source and then just have it source only on one single frame, the first frame of the sim. So either method works fine for this case, because I'm not actually using age or ID in this case. So I'm going to use this. But you can use a pop source, but just make sure that you only source on one frame. And then that's it. So nothing else different here. We've just got our pop solver at default. I haven't changed anything here. But then I did take, so let's just take this out. You'll see here that I have a pop force. I'm not even applying any force to it at all, but simply just some noise. Okay, so if we click play now, you'll see that my particles just kind of move outwards with some noise. Okay, so that's what we have at first, and that's what's giving that kind of swarming noise look. So you can basically you can apply whatever forces you want to this. You could even have it if there are maybe birds trying to form a shape, like flock together and form that shape, but they're getting blown off course. You'd have the node here, which is trying to make them follow, which I'll show you what it's doing just now. So you could have your follow node, but then you'd have this pop force where maybe they're being pushed off toward the side. So, we'd have like quite a strong sort of sideways force, and they're sort of being blown off course, but they're constantly trying to fight to get back to the center, right? And you'd maybe want to animate this a little bit, like animate the way that maybe the strength of it, or how strong each particle tries to follow, so that you can see some of them are fighting against the wind and then they get pushed back a little bit. So there's a lot of cool things you can do here by just applying whatever external forces you want, and the follow force here is going to be fighting against that. Now let's dive inside and see what this is doing. Before we go inside, though, I just want to point out that on the outside, under inputs, I've set my second input to be the second input of the DOP as well, okay? Because we don't have multiple inputs here, right? Like actual reference geometry. But when we set it here to say second context geometry, what that means is at the top here, this second input counts as the second input of this VOP as well, right? So if ever we refer to input 1, which is, remember it's 0 base, so 0, 1, 2, 3. So 1 means the second input. Well, then that refers to whatever is plugged into our DOP, which in this case is our moving sphere, right? So that's our target position. Okay. So with all of that in mind, let's have a look at what's happening in here. Now I'm going to disable a few things, and I'm going to walk you through the basic setup and then the more complex setup. So all of this is part of the more sort of complex bits that we'll add on later. So I'm just going to disable all of this so we can talk about it just now. Right. So what we're essentially doing is we're wanting to take the point position, the current position, and then the target position, and figure out a vector between them. Like how do, like basically where am I and where do I want to be? Therefore, how do I get from here to there? Okay. And we know from what we just discussed in the vector class is subtraction is the way to do that. So now P here is our point position of our points in our sim. Okay, so our actual current point position. But here I'm using an import point node set to second input, grabbing P. So that is essentially grabbing the target position. Okay, and all I'm doing is taking those two and subtracting them from one another. Okay, so we can bypass all of this if you want to be more clear about what we're doing here. So ultimately we're simply just taking our target position minus our current position in order to get a vector from where we are to where we want to be. Okay, so that's this here. This result here, this yellow line, is our resulting vector to get from one area and to another. Okay, and all I want to do is essentially add that to my velocity. So I've got my velocity here, which these points have velocity because they have a force being applied to them. Okay, and I take that velocity and we want to, okay, I'm gonna talk about what's happening here just now, but we're just simply adding that difference. Okay, so we're saying you're here, but we want you to be here, so just add that in as velocity. Okay, and if that's all we did, so let's even disable everything else. Okay, so the only thing that is literally happening right now is essentially target position minus current position to create a vector between them, and that vector is being added to our velocity. Then this is what would happen. Okay, so as it moves, you'll see it's very strictly following. Okay, but it's also doing something a little bit odd. I'll have to jump out to sort of show you the difference between where our target is and where our points are ending up. So they are following, okay? They are doing kind of a good job of following, but they are kind of doing a little bit of an odd thing as well. They're following slightly too strictly, which is something that doesn't look very natural, but they're also overshooting the position by quite a bit. So whenever they sort of try and follow, you see here it starts to follow, but then it shoots right past. And then here it's going way past, and it's having to kind of constantly recalculate itself. And especially here, a tight corner, it really accelerates and goes well beyond, and then it never really settles down. And this is obviously not what we want. And that's the first step I'm doing here. Is all I'm doing is taking this velocity that I'm adding on each frame, and I'm writing it out in its own attribute. Okay, because velocity is an attribute that is being worked on by the solver, so we don't want to overwrite that value. Like, well, we know that value is going to be overwritten and altered by the solver, so we can't reliably store information in there. So we create our own velocity, which is just the previous velocity. Okay, so the previous frames follow force, right? Which is what we're calculating here, and we just store it. Because if we store it, then on the next frame, when we come back in, we can read in what the previous frame's follow force, so the follow velocity was. So we look at what the previous frame's velocity was that we were manually adding in, and we negate it. Okay, so remember, if we negate something, we're essentially subtracting. So here I'm adding a negated value. So ultimately, I'm subtracting the previous frame's velocity from the current velocity before I add in the new frame's velocity. Okay. So what this is basically doing is isolating the natural velocity of the sim from our follow force. We store the follow. On the next frame, we read in the previous frame's follow and subtract it. So what comes out here is the amount of velocity that is sort of just being added by the normal noise and all of, everything else in our sim. Because then when we add back in our force, we're not adding in double force. We're not adding, we don't still have the previous frame's velocity plus some new velocity. We're subtracting it from the previous frame and then adding in the new frame's velocity. But when we add it in, we overwrite this value so that on the next frame, we subtract it from the velocity before adding in and so on. And it kind of loops that way, right? So now with that simply added in, you'll see that we get a very different result. So let's have a look here what's happening. Okay. So it does start to follow, right? Now it obviously is not following quite as strictly anymore, but you'll see it at least isn't overshooting. Now we'll obviously fix the fact that it doesn't follow very well anymore, but at least we don't have it overshooting. So let's jump back in, right? So that's step one. Now let's have the particles let's have them follow better, but also have some of them follow not quite as well. So all I'm going to do is take this velocity that we're adding in and just kind of give it a random different value, okay? Because right now they're all following exactly the same amount, and that really doesn't help us, okay? So if we have them all follow just randomly, so I'm going to switch all of this on and plug this in here. Okay, so you'll see, so you can just ignore this for now. What I'm doing is taking a random value from our point position. So every point has its own random value. I am then putting it through a power function, okay? And the reason for this is to kind of create, like I've said to you before, power is always used to give sort of an exponential kind of fall off. When we create a random value for all of these particles, right, and they've all got it, random is always a 0 to 1 value, okay, then we've almost got an equal number of values that are close to 0 as we will have values that are close to 0.5 and then values that are close to 1. There's like an equal spread of values, but nothing in nature follows like a very exactly equal spread. So what we do by putting it through a power function and setting it to 2 is essentially creating that sort of exponential curve that I was showing you in the previous lessons, right? So it basically means we're going to have more values that are close to 0 than 1. There will be very few that are weighted like near 1 and then more that are all towards 0. And but they still go 0 to 1. They don't go beyond that. But it's just we've changed the weighting of it. And now we put that into a fit. So we go between 0 and 1. We can now make it whatever we want. So here I'm putting obviously our maximums go very, have a large velocity. So some very few particles, because remember there will be more that will be close to 0. Those ones that are close to 0 are going to follow at a 0.5 sort of multiplier, right? So they're gonna lag behind, but a few of them are gonna really follow quite sharply, okay? And then everything in between. Now those are just numbers that I found to work kind of well in my sim, obviously depending on the scale, the velocity, how you're moving it, the sharpness with which your animation changes. All of that will determine how you want to fiddle with these two numbers here, okay? We're ultimately just making all the particles move either more or less strictly, okay? And by doing that, we're just multiplying our vector by a float, okay? And as I've said before, with vectors, so multiplication, the order doesn't matter, but in Houdini it does matter because your first input determines this type of the output. So the vector, we have to put the vector first so that we have a resulting vector, and then we multiply by a float here, which is essentially just changing the length of that vector. Okay, so now when we have it follow, let's have a look at our original. Okay, so as it moves, you'll see that some follow very strictly and others don't. okay? So we will get it to be a little bit more strict and perfect just now as well, but you'll see here that we're at least getting a kind of a better result there. Right, so now let's jump in. Now, one of the things I notice here is that when it moves really fast, we get it stretching a lot. But obviously, if this was a swarm that had some kind of intelligence, when a thing starts moving very quickly, you know, like if you're in a tour group, you know, like a tour guide is kind of leading you through a museum or something, and if the whole group started moving really quickly, you wouldn't just kind of amble along behind at the same kind of speed. You know, like some people follow more strictly, some people like to linger and lag behind. That's fine. But if the group really started rushing, like there was a fire in the museum and people started rushing out, everyone would move a lot quicker. Do you know what I mean? So it's like, sure, some are a little bit slower than others, but when stuff starts speeding up, you expect it all to speed up, okay? And so just a straight multiplier doesn't really give us that result. So what I've done is I've taken the length of the difference between our position and our target. And as that value gets longer, I want to multiply by even more. Okay, so I'm essentially taking that length and multiplying our random amount by that length. So the further away I am from my target, the faster I'll move to try and catch up. But then as soon as I get closer and closer to it, I then can kind of slow down, and I'm like, oh, well, I've caught up to the group, so now I'll linger behind because, you know, I like to linger behind. Whereas our strict particles are still going to remain strict. And in fact, the faster it moves, the more strict they become. Those that are lagging behind will always lag a little bit. But as it speeds up, then they start to kind of, you know, follow along a little bit more strictly. And then when everything slows down, well, then you see they slow down as well and they really linger along the outer edge. Okay. So that gives us quite a nice result, right? But something I just want to make a few adjustments here. One thing is that I don't like them following the sphere perfectly. Okay, the sphere is almost like their target. It's like the hive, but they don't need to literally be attached to the hive. They need to be slightly away from it. So when I'm sourcing in my points, I'm also grabbing the normals from the particles. Remember, I calculated the normals on the sphere over here so that we have these kind of outward facing normals on our points. And all I'm going to do is add, right? So forget this multiplier here. So we're just adding in our position with the normals. Okay, so now remember, adding two vectors is going to result in sort of moving outward along those normals. So point position plus the normals is my target. I don't want to target the position itself on the sphere. I want to target a position slightly outside of that. Okay, so you'll see here the sphere is now slightly expanded that we're following. Okay, if I actually show my original sphere, my animated one over here, you'll see that they do follow the sphere, but they don't try and attach to it. They just follow a radius around the sphere. Okay, right. So that's what I wanted, the result I want. But I also notice here that you see that as they start moving, this looks really odd, because when something starts moving and you're lagging behind, you don't really generally try to also maintain a perfect distance from it. You're already behind. You already have a distance. So as it starts moving, I'd expect them to kind of almost the stream of them to narrow as they're trying to follow and catch up. And only when they've caught up do they then go kind of outward and maintain their distance from the hive. So what I do over here is I'm then taking essentially the velocity of our target. Okay, so I'm measuring sort of the velocity of how fast our target is moving and taking the length, because the length of that velocity, right? We're going to discuss length in the next lesson in more detail, but essentially the length of the velocity is the speed. In other words, we don't care about the direction, but just the magnitude of it. How fast is it moving, right? Now I'm binding the speed out here only for my own visualization purposes, okay? So we can go, and especially if I go out here so it's easier to see, I can have a look at my speed, especially if I'll just type it in here so we can see the speed, and we can let it go over, over the frames and kind of see what our general speed is. Like, what's the maximum and minimum that we're ever moving. Here we're moving at about 16 units, 17, 18, 19. That's about the maximum I see there is about 19, okay? So I use that as a way to know what range we're working with. So now when we go and fit, I can kind of see fit between certain in range. So maybe go here between 0 and 19. And now I'm saying when it's traveling 0, so in other words, when it's not moving, my target is not moving, then I'm going to multiply by 1. So in other words, you should be following, maintaining your distance, because what I'm multiplying here is the normals. Okay, I'm going to multiply the normals. So my normals are multiplied by 1 means when it's not moving at all, yes, respect the normals. In other words, maintain a distance from the hive. But then as soon as it tends towards a speed of 19, so as it starts traveling faster and faster, then you start ignoring the normals more. So you multiply the normals down to 0. So now our target is the hive itself. We want to literally get to the center of that sphere. But then, well, not the center of the sphere, but the surface. Like literally we want to touch the surface, the faster it's moving. But then as soon as it slows down, we remember that, okay, hang on, I don't want to actually be on the surface of the sphere. I just want to maintain a distance from it. Right. So we then multiply our normals by this float. And again, it's a vector multiplied by a float. So we put the vector first because we're just wanting to alter the length of that vector. See, if I alter the order of this, because the float is first, the result will be a float, and that will not give us the right results. You'll see weird, crazy things happening here, which is not what we expect. Okay, so essentially what I'm doing here is I'm saying when it's traveling slow, yes, you have a distance, but the faster you move, you see the stream narrows, and then when it slows down, they spread out again. And I'm just taking that value and again putting it through a power so that we have a little bit of variation and sort of a natural exponential following, okay? So as it goes really fast, yes, it goes thin, but as it's moving just a little bit, they don't really start to immediately thin out the stream, okay? And that's our whole setup, right? So it's very basic. Obviously, when you look at a setup like this, it looks quite complicated, but if you look at it really like the basics of what it's doing, we're ultimately just calculating the difference between current position and the target position, okay? And we're using subtract to calculate that. But then we're just multiplying and adding and doing all sorts of things to that value so that it is a bit more natural. Some of the particles follow better than others. They follow more when it's moving faster. They try to maintain a certain distance from the hive, but when it moves faster, then they forget about that and they just try to catch up. And then ultimately the real trick here to making it look nice and natural is to subtract the previous frames follow before we add some more, because otherwise we're just going to add velocity every frame and that just looks terrible. Okay, so you'll see what happens here if I switch that off again, but with everything added in. It does really bizarre things, and then because it keeps overshooting itself, it tries to catch up to the hive, but like completely, and it overshoots, so then it turns around and goes through, so it looks really crazy. Okay, I mean, maybe that's the effect that you want, but if you wanted to kind of sort of like maintain a nice gentle, they get to kind of just swim around, and then when it starts moving, they go, oh, whoops, I need to sort of catch up to the rest of the swarm. And then when they do, then they just settle into doing their own thing. Yeah. So this is an effect that I've had to do quite a few times because there's often some kind of thing, whether it's bees or birds flocking to do something, or even just something like magic, that little maybe fairies or sparkling lights that sort of follow something. Obviously, depending on how strict or loose you have it follow, then you can achieve some very different results. Okay, so I hope you found that useful, and that you see how the sort of adding and subtracting and multiplying of our vectors is very useful, and then also things like using power to make things kind of look a little bit more natural. Right. So I hope you enjoyed.